how much area I should put here. Actually, according to that formula, you can determine, because IYY should be that one. Use that formula equal to this one, you can determine what is A. This is how we make approximation in wing structure and fuselage structure. I'm going to show you some examples. And this is for IZZ. You assume some area is carrying the normal stress. IZZ should be this one, right? This A is unknown. All of the other things are the geometry parameters. So you can figure out what kind of area should be. And according to this, maybe you can immediately have an idea. This approximation is not unique. What if I put an area here? What if I put an area here? Right? It's not unique. You can assume according to your convenience. I mean, you can make another stick model like this. Right? You have some other A. 6 boom areas. And in this case, the value of the boom area will be different from this one, right? Because you have to guarantee IYY, IZZ is still the same, but you are using more boom areas. So that means this approximation is not unique. You can determine this for your convenience. And in our homework or exam, most likely I will give you what kind of approximation I'm going to make. You just do the calculation, because otherwise everyone will have a different approximation at different areas. The solution will be various. So let's look at a wing structure. This is a beam, not a realistic aircraft structure. So let's look at a realistic wing structure. It's not that realistic. This is a cross-section of an aircraft wing, and you have a thickness. Actually, the skin have a thickness, right? So, and you may have some spar in the interior of the wing. Look at that wing cross-section is a shape like this, right? But within that wing, you may have some spar and also stiffener. Stiffener means like this. This is a very simple wing structure. This is a cross-section of an aircraft wing. Within the interior of the wing, we may have stiffeners, we may have some spars, okay, to make the structure more reliable. And if we want to, in this one is we approximated the I-beam as a stick model. In this one, we also can approximate, this is a cross-section, right? We can approximate this wing cross-section as a stick model. So that means we assume zero thickness. There's no thickness of the skin, and also the spar. Okay, this is the first step, and then in each stiffener, corresponding to each stiffener, we can put a boom area. So boom area like this. Boom area, first one, second one, third one. This is so-called idealization. And this one is a stick model of a wing. This is a realistic wing cross-section. So if we define a coordinate here, y, z, then what is IYY, what is IZZ after you idealize the structure? So if you know For example, for the ice boom area, the area of this boom area is AI. And the coordinates of this area from here to here is yi. From here to here is zi. Each boom area has a coordinate in yz coordinate, right? So what is Iyy, what is Izz of the idealized structure? So the formula will be like this. Area times the distance squared. But the first step, we need to move. We need to figure out what is the center of gravity up to your idealized structure, right? Maybe at here, C. We need the first step. Before we can calculate what is Iyy, Izz, we need to figure out what is the center of gravity first, right? So what is the center of gravity up to idealized structure? So YC, there's a formula for YC is summation AI, YI, summation AI. And ZC is equal to AI, ZI, summation AI. This is a coordinate of the center of gravity of the cross-section. What is AI? AI is the area of each boom area. You have many boom areas, right? So corresponding to each boom area, you have an area AI. And each boom area also have a coordinate, has a coordinate YIZI. So this is basically what is meaning of each index. And what is summation on AI? Put all of the areas together, right? Each boom area, sum them together, you will get a value. So, and then what is Iyy? What is Iyy? Is AI times yi minus, sorry, this is z. Iyy equals to area times z squared. This is a formula for the second movement area about y-axis, right? Area times z squared. This is what I have learned in mechanics materials. Area times the distance squared. The distance is z, corresponding to Iyy. And there's a summation. Summation means all of the boom areas. And Izz will be summation on AI, Yi minus Yc squared. So this is the first step. This is the second step. And then the question is, after you do the idealization, the objective is still to figure out what is the normal stress and what is the shear stress. Right? Basically, the structure analysis is also focusing on what is the stress distribution in your structure. So you need to figure out what is sigma x, what is tau xy, something like this. But what is sigma x? If we look at the formula that we have, maybe we do not about the boom area first. In 321, we have a formula for normal stress. It's very long. I have to copy from the notes. It's Iyy times mz minus Iyz times my divided by Iyy Izz minus Iyz square plus Izz my minus Iyz mz Iyy Izz minus Iyz squared. This is a normal stress distribution in a beam cross-section when you apply a bending loading on the beam. Basically, you have, imagine the wing as a beam, okay? This is a cross-section, imagine the wing as a beam. This is a cross-section of that beam. You apply mz and my, this is y-axis. You apply two bending loading on that beam. You will introduce the normal stress into the cross-section, right? What is the normal stress? Formula? This is a formula for normal stress. We learned this in 321, so-called bending of beams. right? If you recall what you have learned in mechanics materials or 321, you will remember something like this. When you apply My and Mz on a beam, this is the sigma x distribution within the cross-section. And Iyy, Iyz, and Izz is a sectional property, so-called second moment area of that beam. Same thing, no matter how complicated the cross-section will be, we use the same formula. This is the idea. The cross-section now is very complicated. Skin stick model is like this, but we are going to use the same formula because we already calculate Iyy, Izz, My, and Mz are the loading applied on the wing, so we can use this formula. I'm sorry, there's a Y here, there's a Z here. Okay, so nobody remember the formula. This is the Y. This stress distribution within the cross section is a function of Y and Z. Each point will have a different sigma x, so that is why it's a variable. Within YZ coordinate, each point will have a different sigma x. So if you do not have Y and Z, it will be a constant. That is not true, right? So this is the formula for sigma x. And then we can calculate the normal stress in the ice boom area. You have many boom areas after you do the idealization. So what is the normal stress in that area? As I said, each area, each point within the cross-section will have different normal stress. So that means each boom area will have different normal stress. So sigma x I, right? Index for the ith boom area. Iyy, I just copy that, Mz minus Iyz My. And Iyy, Izz minus Iyz square here. Why? I. Because you are talking about the ith boom area. You need to use the coordinate of the ith boom area, right? And the second term, the coefficient is same, Izz My minus Iyz Mz minus Iyy Izz minus Iyz square Zi. This is a normal stress in the ith boom area because each boom area will have different y coordinate, z coordinate. And we're going to do an example. So suppose you have wing cross section like this. This is your idealized wing cross section, skin stick model. This is a skin. So this, you put some boom area. The area of each boom could be different. So this one is 2 centimeter times 2 centimeters. And this one is 1 centimeter times 1 centimeter. Okay? And you put your Y here, you put your Z here. Suppose you apply a MZ, a Z-axis, and also a MY about Y-axis. That means this beam is double banded. So with a single banded beam, double banded beam, that means this is the length direction. This is the length direction along the wing length. This is the direction along the wing length. Okay? And this wing could be bended about the z-axis and could be bended about the y-axis simultaneously. So this is the loading. And some geometry from here to here is 0.25. From here to here is 0.5. From here to here is 0.75. From here to here is 1. And the height from here to here, and from here to here is 0.25. And from here to here is that much, and from here to here 0.5, and from here to here is so this is geometry. After you finish the idealization, you know what is the coordinate of each boom area, right? So this is the first boom area along this direction is that much, along the vertical direction is that much. This is the second boom area along this direction that much, along vertical direction that much. So each boom area has a coordinate, and it's symmetry about y-axis. So I only give 1/2 of the geometry. It's symmetry about y-axis. So the question is, if MZ, MY is not 0, MZ is not 0, double banded beam, and nothing else. The question is, what is the force on each boom area? You apply some bending loading on the wing, and must some force be introduced into the wing, right? What is the force acting on each boom area? And this could be useful for you to change your design or revise your design after you figure out what is the force acting on each boom area and what is the normal stress. What is the definition of force? What is the definition of force if you have stress? Stress times the area, right? So force equals to stress times the area. And then basically we need to figure out what is sigma xi. What is the normal stress acting on each boom area? The formula is the one I just give you. Actually, this formula was used many times in 321. IZZ minus IYZ square YI plus IZZ and Y minus IYZ and Z ZI. For each boom area, we need to figure out the force. The first step, we need to figure out what is the normal stress on each boom area. And it is very complicated, right? But when you look at the cross-section of this beam, actually this is the beam, very complicated beam. It's symmetry about y-axis. So when you look at a cross-section of a beam, if it is symmetry about any of the axes, that means IYZ will be 0. Okay? Symmetry, if you have a symmetry cross-section, IYZ will be 0. That means IYZ is 0. So under this, sigma xi can be reduced. Sigma xi, IYZ is 0. So this term will be gone. This term is gone. This term is gone. This term is gone. Right? And IYY will be cancelled. Will be cancelling with IYY here. So the first term will be MZ IZZ YI plus second term MY IZZ cancel with this IZZ, so it's MY IYY ZI. This is a reduced formula after you apply the symmetry condition of the cross section. And then each boom area you have a coordinate. That means YIZI is there already. And MY and MZ and MY are given loading. You do not have to worry about it. So in order to figure out what is the solution, the only thing actually is what is IYY and IZZ. And what is IYY? Summation AI ZI minus Z squared. Right? And what is IZZ? summation on AI yi minus y bar squared. We need to figure out this too, and then this sigma x can be solved. So what is IYY? Each area, each boom area, you know what is area? 1 times 1 centimeters. So some of them are 2 times 2. So don't worry about it. It's given. Each boom has an area. It's given. It's already there. Each boom area has a coordinate zi. It's already there. So we need to figure out this z bar and y bar. It's not y bar. I use yc, zc in the previous notes. It's the center of the gravity. The same thing. Center of gravity. So zc, maybe to be consistent, I use yc, zc. The center of gravity or the cross section. This one will be ai zi times ai. Right? This is how we are going to calculate zc. And then we come back to look at the cross section, because now we need to calculate what is center of gravity of this. So this is a cross section. Each boom area, this is a boom area. Each boom area have a z coordinate. So we do that one by one. The first one, the area, AI, or the first area, is 1 centimeter times 1 centimeter. Only 2 different areas in this setup. Okay? The smaller one are 1 times 1. The larger one is 2 by 2. Okay? So the first area is 1 centimeter is 1% meter, right? 0.01 times 0.1. This is the area of the first boom area. And then times the coordinate of the first boom area. This area, this is a coordinate. It's negative, right? So negative do that one by one, right? And what is this one? It's the total area of all of the booms. So the first one, this is the area of the first boom. And the second one, second boom, same area, right? And this one will be different. It's 2 by 2. So you just do that one by one. You do not have to do that calculation. What is the value of this one? What is ZC for this cross section? 0. It's symmetry about y-axis, right? Because this one times the negative thing, when you come back to this one, it's a positive something. It will cancel, right? So it's symmetry. All of them will be canceling with each other. So ZC will be 0 actually. YC will be different. YC is along this direction. So YC will be different. But this is a formula. This is a formula how we're going to calculate center of gravity. Then YC equals to AI yi summation on AI. First area, same thing. This is the area of the first boom. And y coordinate is, when you look at the cross section, y coordinate is from here to here, right? It's 0.25 from here to the first boom along y direction. And second one is this area, same area times from here to here is 0.5. And you have many areas. Actually, you only need to do 1/2 of this one and times them by 2. They'll be the same, right? All of the areas above y-axis will be the same as all of the areas below the y-axis. So divided by total area, the first one plus the second one plus many of the areas. You have more than 10 areas. To put them together, you will get a number. So what is number? What is YC? 0.861. This is coordinates for YC. That means from here from here to here is 0.75. You get 0.861. That means something here. Right? It's in between 0.75 and 1. So your center of gravity will be at here. This is how we calculate the center of gravity. And then, basically, this question can be solved very easily. You figure out what is YC, ZC, and you go back to figure out what is IYY. ZI minus ZC squared. Right? ZC is 0. ZC is 0. This one becomes AI, ZI squared. And then, what is this term? We have many terms. Each boom will have AI. Each boom will have a ZI. So many terms. And the first boom area, this is the area of the first boom. And what is ZI? The first boom area is at here. And ZI is from here to here. The coordinate of the first boom along Z direction, it will be this much. Right? You have a square here. And then you come back to the second one. The second one is this one. And it's 0.25 squared. So this one from here to here along the coordinate. Right? So you have many terms. Just do a simple summation. You can figure out what is IYY. You have a question about this? Question? Second one? This one? So basically it is this is from here to here is 0.0625. This one is the second one. From here to here is this one. Here. This one? You're right. Sorry. This one is 0.125. This one is 0.125. I dropped one. Thank you. So if you have some questions, just stop me. Thank you. So this is 125. I dropped 1. That makes sense, right? Because this is should be doubled this number, right? 1/2 of this one. This one should be 3 times of this number. So that means this one should be 0.125. And do the same thing for IZZ. IZZ will be AI YI minus YC squared. YC is this much. Okay? So you have to use that formula AI YI minus 0.861 squared. And then do that area by area. IZZ. So I will give you the example for the first area is this much. Minus .25 is YI. The first area, the coordinates along Y direction, minus YC. And you will get IZZ. IZZ equal to 155 10 to minus 4. This is IYY. This is IZZ. Okay? And then we come back to use sigma xi. Because we need to figure out what is force acting on each area, we need to figure out what is stress first. Sigma xi equals to mz yi IZZ plus MY ZI IYY. This is a normal stress acting on the ith boom. And you already calculated IYY and IZZ. This loading is given. It's non-zero, it's there. Don't worry about what is the number, just put it there. If you know the number, just plug in the number. Okay? So for each boom, you have a YI, ZI coordinate. And then, for example, for the forced boom, sigma x1 will be mz. IZZ is 1,485 10 to minus 4. And yi, for the forced boom, yi is forced boom. What is y? 0.25, right? 0.25. And my, and plugging IYY is 10 to minus 5. ZI is a coordinate of the forced boom. Z1, actually we are talking about the forced boom. So Z1 is negative. This much. YIZI is a coordinate of each boom. So basically you just use the coordinate correctly, you will get the correct number. And then what is the force acting on the forced boom? Will be sigma x1 times A1, right? Stress times area. So sigma x1 times the area of the forced boom. This is how we calculate the force acting on each boom. Basically, this is the question. What is the force acting on each boom area? So you can do that one by one. Second boom, third boom, it will be the same thing, right? The only thing that is going to be different is for the second boom, you have to use the coordinates of the y2 and plus my z2. y2, z2 is the coordinate of the second boom. So basically in textbook, you will see a table about this. At least they construct a table for each boom and calculate the normal stress on each boom, put it in a table. It's the same thing. You just do this by hand, one by one, it will be okay. Okay? So this is very straightforward and very simple. And for wing structure, we can do this. Same thing for fuselage. We also can do this idealization and figure out what is normal stress. And I'm going to stop here actually. Time is up. I'm going to explain one more example in textbook. It's on page 583. If you have textbook, you can read it. Fuselage. This is a wing. Okay. And please put your homework 2 on this table.
I was just sitting here trying to think about how what I need to do for it. It feels so freaking good. After getting 2 freaking hours of sleep. That's so nice, because that's tomorrow. Dude, you shouldn't have gave it to him.
I didn't realize this.
Do you remember when we left the computer lab? Or when we were in the computer lab like midnight? He's like, how do you do this? And we told him it was a lengthy process. He's like, oh yeah, fuck that. You know, I'm at like midnight, went to sleep, then comes in and is like, hey, can I have your K matrix? Like, fuck you, dude. That's why I was like, no, I'm gonna go turn mine in, see ya.
I will set different problems for you. Yeah.
That pissed me off.
It's the same one, right? Yeah. What is that?